And the second question is, oh, I see. I seem to be a typo factory. So let's just see about that. Well, there's 12. I don't understand. I've got homework 10, homework 11, homework 12. Whoa, homework 13. Yes, okay. Boy, you guys are great. So let me get the right one. So this is 14. Save. Move to the computer. All right, now it should be correct on the office computer. Okay, now so thank you for correcting that. Now, problem 2. Okay. Good question. So we have a particle of full momentum and mass, full momentum P, mass M, absorbs a photon. All right, so let me illustrate this with a Feynman diagram. So what we've got is a particle coming in, and it absorbs a photon and carries on. Okay, now the question is, let me go back to here and switch to blue. Or in fact, let me erase this. I'm switching now to blue. The question is, can the blue particle be the same kind of particle? In other words, this particle, let me switch now to black. Here, this particle has mass m. This is a photon. And the question here is, can this particle have mass m? I'm thinking here of particles that are of spin 1/2 or spin 0. Let's think in terms of spin 0 more simply. Can it have mass, the same mass? That's the question. Obviously, it has a different fall momentum, but can it have a the same mass? And shift the question page. Well, for one thing, I can make the question page much smaller. And I guess I can even put it over here. Is that what somebody said? Shift? Okay, well, so thank you for all these corrections. It's just wonderful to be to have my mistakes corrected and fixed by students. That's great. What I forgot to say in the statement of the problem, but which I kind of tacitly assumed that everyone would use, and it's conservation of momentum and energy. So use conservation of form momentum. So energy and momentum are conserved in physics, and in particular, I mean, in cosmology, you have some people saying that energy is conserved, other people saying it's not. But I side with Guth, who says it is, and I think he's right in, well, in Dirac discusses this also. But anyway, when it comes to small scales, laboratory experiments, energy and momentum are conserved. And so you use conservation of form momentum. And so that's that. So now let's see. Let me go over here. Hold on. I think we were talking about this, but let me actually go back a little bit. I rewrote for the second time the chapter on, I've moved the chapter on affine connections, on the affine connection, and I've now put it earlier, and I'll put this on the class website, I hope correctly. And so I'm starting out by defining the Christoffel symbol of the first kind simply this way. It's the dot product. And of course, the dot product is understood when we're talking about basis vectors or tangent vectors. They're dot products in the semi-Euclidean embedding space. So it has one or more minus signs and then all plus signs, and it's completely diagonal. So this zeta here is something like -1, and then 1, 1, 1, and so forth. So it looks like that. And it's just like the Minkowski thing where eta is -1, 1, 1, 1. So what we have here then is the ith derivative of the ith tangent vector. Well, the ith tangent vector is the partial of the point on the manifold with respect to the coordinate xi. And then if you take the ith derivative, you have a second derivative here with respect to L. But this is the same thing as the differentiation in the opposite order. And doing it in the opposite order, we get that we've got the ith partial derivative and the ith partial derivative of the ith partial derivative of the point P. Anyway, that means that that if we define the Christoffel symbol of the first kind this way, we can write it as 1/2 this by just interchanging L and I. These dot products then, since G, I should have written this as IL, so let me just write that IL. So this is the ith derivative of GNI minus this term here, where the derivative acts on this tangent vector and leaves that one alone. Similarly, you can write the second combination this way. And when you do that, you can write the Christoffel symbol of the first kind this way. And then if you use the fact that n comma L is the same as L comma N, and n comma I is the same as I comma N. And then a dot product En comma L dot EI is the same as EI dot En comma L because dot products are symmetric. We can rewrite that in this form. And now we see that this is just the nth derivative of the metric GIL. And now if you just raise the index n, you get a Christoffel symbol of the second kind, which is what we've been calling the affine connection. So I put that forward, and then the affine connection can be used directly when we create the covariant derivatives. Okay, so that's one thing that I did, and now I was thinking of skipping to there, but if does anybody have a, well, we've got this chat box working here, so feel free to ask questions, to ask me to explain something, or to say that you'd like me to shift the discussion to a different section or even a different chapter. If you have me talk, if you want me to talk today, if you want me to talk today about a different chapter, that means I'll be winging it, but that's okay. So
please discuss the FLRW metric. It is important.
Let's see, I was unable to understand that. Could you please use the chat box, because I'm hard of hearing and Zoom is not totally reliable acoustically. Okay, so these models of cosmology, which actually were developed many, many years ago and what we're still using, they treat time the way Aristotle treated time. In other words, there's nothing sophisticated about the way we're treating time. And for space, what we say is space has been expanding according to a scale factor, which we call A of t. And at the present time, we're going to set A of t equal, or A0, whoops. We're saying that the scale factor is A of t, A of t0, which is A0 is equal to 1. T0 is something like 13.8, 10 to the 9th years. And I'm not going to throw that into seconds. Actually, it's not that hard, because it's essentially then pi 13.8, 10 to the 16th seconds, because a year is roughly pi times 10 to the 7th seconds. Anyhow, okay, here's a question on the chat. All right, it's a question about the Christoffel symbol, and I assume this is not a homework problem, right? This is just that you want to understand general relativity more completely. Is that right? When I turn my head to, okay, thank you. Well, I don't know, but in general, I mean, it depends. It's a question of taste. If you want to allow for the possibility of K, this parameter here, not being 0, then of course you have to keep it. But on the other hand, you can say, okay, we are going to do cosmology only in the case k equals 0, in which case you set k equals 0 and you don't keep k. Notice that experimentally, k is consistent with 0. It may not be 0, it could be slightly positive, slightly negative, but it's very small. And here I'm just summarizing the consensus among astronomers and physicists from observations, both astronomical and, of course, of the cosmic microwave background, which has given so many results, and which, of course, was totally unexpected. Well, I shouldn't say it was totally unexpected. Some very bright physicists years ago, almost like 90 years ago, thought that the universe started out hot and realized the universe started out hot and predicted that there would be some sort of cosmic microwave background radiation. So what we do in these cosmologies is we treat time, as I said, the way people have always treated time, and we just include a scale factor A, which at time 0 was 0, at time now is equal to 1, and in between was expanding. And then we say that from astronomical observations, the universe on large scales, which is what we're talking about, is homogeneous and isotropic as far as we know. And so what we do is we put in, for the space part of the metric of a maximally symmetric three-dimensional space. There are only 3 such spaces. One is flat Euclidean 3 space, that's k equals 0. The other is the curved surface of a three-dimensional sphere, the three-dimensional surface of a sphere in 4 dimensions. In other words, the 2-dimensional surface of a sphere is the normal sphere that we talk about, that's just an ordinary sphere in 3 space. Well, if you take space, 3 space, and make it 4 space, and take the sphere, the 2-dimensional sphere, and make it a 3-dimensional sphere, then the surface then is 3-dimensional, and it's maximally symmetric. And then the other one is a hyperboloid, which can be embedded in a 4-dimensional space-time. And if you combine the space-time of the hyperboloid with our time, you then have a semi-Euclidean space with 2 time dimensions and 3 space dimensions. On the other hand, for the case k equal to +1, that's the surface of a sphere, and so the embedding space is semi-Euclidean with 1 minus sign and 4 plus signs. The 4 plus signs are the 4-dimensional space that you fit the 3-dimensional sphere in. Okay, but as I say, it appears that k is 0 experimentally, which has been a source of great disappointment to cosmologists, because to gravitation, to people who have given their lives to the study of general relativity. Such people are, I think, rather disappointed that the universe turns out to be pretty flat. Anyway, one way of computing these connections or Christoffel symbols of the second kind is that one says, well, let's use as our action principle, instead of something with a square root, let's just use GIK and then dxi with respect to, say, d lambda. Lambda is some scalar that describes the path. So you've got some path through space-time, say, and lambda is just, here's lambda equals 0, here's lambda equals 10 or whatever. And if you then, actually, I think there's a typo in this equation. Yeah, I don't think there should be a D there. So let me, all right, I'm not going to fix this in real time. But I think this is a typo. I think this D should not be there. Anyway, you can then say, take the variation of this and what you'll get if you do the T variation, the variation with respect to T of lambda, then you get this equation. And well, you know something that's T double prime there has to involve this Christoffel symbol because we worked that out earlier here. Let me maybe flash back to there. In other words, if you use this action principle, instead of the one with the square roots, you get this expression on the right here, which is simpler. I think probably I should have done that one in the text. Whether you use something like this or the other, you get the same equations of motion, because if you say S1 is an integral, say, of square root of minus, there it's GIL XI prime XL prime d lambda. The primes mean d by d lambda. Or you say S2 is the integral of minus GIL. The overall minus sign doesn't matter. Suppose we vary S2 and set it equal to 0, we're going to get the same equations, because we're going to get, this is going to be minus a variation of all this d lambda. And on the other hand, if we do the variation of S1, what we're going to get is 1 over square root, and in fact 2 square root. And then up here, we're going to have minus the same variation, d lambda. And now this is an overall factor that isn't going to make any difference. So we get the same equations of motion. And this gets us to this makes calculating the connection, the affine connection, easier. Maybe I should do the case. Let's do the case, say, where suppose we vary phi, which is the simplest case. So we go back to this expression up here, and we're just going to vary phi of lambda. And let's see, I haven't done this in so long, I don't really remember. So we want to say here, 0 is the variation of minus c squared t prime squared plus a squared r prime squared. This is, I think, going to take too long. And so if we go down here and we're changing phi, then oh, I'm going to stop because I haven't done this in a couple of years, possibly 10 years, and moreover, even if I did work through it correctly, it would be it would take a while, too long. Anyway, one gets this equation, and one then compares this equation with the same thing with phi double prime and affine connection terms here. And so then one gets the various coefficients, this one being cotangent theta, this one here being 1 over r, and then this one being a T phi case. Once one has gamma, one can then compute the curvature tensor, and then you take a contraction of the curvature tensor, and you get the Ricci tensor, and that's what you need for Einstein's equations. Now, one of the problems in general relativity is that space-time has 4 indices, even when you forget about the embedding space. It's 4 indices, and so you have so many indices, and the equations are very complicated. So it's very time consuming to work through them, and you can make mistakes. And so it's useful to use computers, and perhaps if you have anything that's non-trivial, it may even be essential to use computers. I tell you what, I will look into the possibility of, okay, I see a question on the chat screen. I'll get to it just in a second. I have a script that works in Mathematica, but not all of us have access to Mathematica. And so what I'm going to try to do is I'm going to try to find an equivalent script for MATLAB. In fact, some of you may know of a script that works in Python. I'm sure there are scripts in Python. I just haven't used Python enough to know what they are. Lambda is simply a parameter, and a parameter that labels, let us say, its distance along the curve. So it's kind of like time, and it's also kind of like proper time. But basically, it's a scalar parameter. Time is not a scalar parameter, but proper time is. Along the curve. So I wouldn't call it a variable, I'd call it a parameter. I tell you what, on next week, I will come back. I will do this in more detail next week. I hadn't thought of focusing on it today. Anyway, in order to, once one has the left-hand side of Einstein's equations, which are something like RIK minus, I think it's a half GIK R equals. Now, let me see if I've got that right. Goodness, I don't know where it is now. Oh, Lord. All right, Einstein's equations. Yeah, RIK minus I have GIK R equals, and then on the right-hand side, we have 8 pi G over 3 times TIK. So you need to know what TIK is. Well, what people do is they make a model of the universe in which there's as little complexity and as much symmetry as possible. And so they imagine that the energy momentum is that of a perfect fluid with a certain fall velocity, a certain mass density, rho, and a certain pressure. And the energy momentum tensor for such a perfect fluid then is given by this expression here. I suppose I should derive that at somewhere in the book, but I didn't, I don't think. Anyway, the fall velocity, of course, is dxi d tau. And if we're in co-moving coordinates, so the co-moving coordinates, the idea is that you've got an early universe, which looks, if we think of it as a surface of a sphere, looks like that. And then at a later date, it looks like this. And so then 2 points here look like that in the universe there, and then they look like this maybe at a later time. But what's happened between here and there is that A has increased, whereas the coordinates here of the blue dots have not changed. And so in co-moving coordinates, the DXIs, the spatial part, the ordinary velocities are 0, because the idea is that that space expands and the points aren't moving around apart from the change in the scale factor. Those are called co-moving coordinates. And in those co-moving coordinates, the UI has a very simple form. It's just time going forward. And so when you substitute that U into there, you get this expression, and then you can find the trace and so forth. Then you finally have, if you've already computed the Ricci tensor and the Ricci scalar, you already have then 2 equations. That is to say, Einstein's equations give us, well, they're obviously the Einstein equations here are 16 equations, but they're not all independent. And when you put in what the Ricci and tensor and the Ricci scalar are, they collapse into basically 2 equations. And you've also made the energy momentum tensor as simple as possible. They collapse into 2 equations. And then if you subtract this one from that one, you get rid of the acceleration term. and you get a really nice equation, which is the first order Friedmann equation. The left-hand side, what you have is the Hubble rate squared. And so you have this rather simple expression here. And if you then divide both sides here by, well, first of all, there's this critical density. What's the critical mass density? The critical mass density is the one such that K would have to be zero. It's the mass density that a flat universe would have, or the mass density that would make the universe flat. So in other words, if 8 pi g over 3 rho is exactly equal to h squared, then whatever somebody wanted K to be, it's gone because it has to be zero. That's called the critical mass density. And so then if you call, people call omega the ratio of the actual mass density to the critical mass density. And when we say mass density, we mean the energy density of empty space divided by c squared, the mass density of dark matter, the mass density of ordinary matter, and the energy density of radiation divided by c squared. And so it all gets converted to a mass density. And you take the ratio of that to the critical mass density, and that's something called omega. Now, for the last 40 years or so, some physicists have been saying omega is 1, and astronomers have been saying omega is 0.1 and or 0.01. And it turned out the physicists were right. As far as we know, omega is 1 or very close to 1. And but as you know, the 2/3 of omega is dark energy, and only 1/3 is matter, and of the matter, most of that is dark matter. Now, if you use conservation of energy, so where am I putting in conservation of energy? Well, first of all, yeah, it comes from this equation that the 4 divergence of the I = 0 component of the energy momentum tensor vanishes, then what you get is this equation here, that 0 eventually is rho dot plus 3 a dot over a rho plus p over c squared. And that gives you some nice equations, which I think play a role in some of the homework problems. And so initially, this equation is exactly that. And if instead we divide both sides by a dot, then we get d rho dA is equal to this. And in these simple models of the universe, we say that the pressure is related to the mass density by an equation of state. And we say that equation of state is pretty simple for each component. And the mass density of each component is called rho I, and it has its own pressure related to Wi, P rho I, Wi being a constant. Now, so then the total pressure is the sum of these summed over I. And these assumptions are made to make the calculations as simple as possible. It's possible they're also been made too simple. There are 3 kinds that are important, of course. There's the mass density of dark energy, and that we think of as, we think of that as being essentially a cosmological constant, and like the energy density of the vacuum. And so it's independent of the scale factor. And so we just set W equal to -1. And so then it just doesn't change. The mass density of the vacuum doesn't depend upon the scale factor at all. For matter, the mass density falls as the third power of the scale factor because because the universe is expanding. And for radiation, when the scale factor expands, the momenta of the particles are redshifted. And so that's an extra power of A. So altogether then, the mass density is a constant from dark energy, a 1/A cubed for ordinary and dark matter, and a 1/A to the 4th for radiation. And one then puts that into rho and into the first order Friedmann equation. You divide by h0 squared, you get, and do some manipulations, you get something that looks like this. And what you can say then is this is omega lambda, this is omega matter, this is omega radiation. A0 is automatically 1. And you can compute, all right, there's a question here. The W equals, it's a question about W equals 1/3. So, well, the thing is, if you set W equal to 1/3, first of all, let's go back to this one. If you set W equal to 0, well, why do you want that? Well, the pressure is 0 for these, we're imagining that matter is just not interacting, and consequently, it's just dust particles gradually moving farther apart because of the expansion of space. So the pressure is 0, so W is 0. And then that gives you, if W is 0, a rho is just 1/A cubed. With radiation, it's not that you compute W equal to 1/3, it's that you know that the density of radiation is going to go down as the 4th power of the scale factor. And so you choose W to be 1/3, because then you have 4/3 here, the 3's cancel, and you get 1/A to the 4th. So that's the logic there. On the other hand, you can also just imagine that you have a photon moving along a geodesic in an expanding universe. And if you do the calculation, you see that the momentum of the photon is reduced by a factor of 1/A as the universe expands. So let's see, where was I? Right, so of course you can compute this energy density of the photons, and one way of doing it is to measure the temperature of the CMB. And that's been measured extremely accurately. And one of the remarkable things about the CMB, as I mentioned to you once before, is that it is the most perfect black body anyone has ever seen. And people thought it might be something like a black body, but when it was finally measured, it turned out to be exactly a black body. And so what you can do is say, well, if you have a universe at this temperature, how many photons are there going to be? Well, that's the Planck distribution, which was discussed in chapter, I don't know, 4 or 5. And you can then compute what the energy density is, and it winds up to be this value. let's see, you want to then, so this is what you get for the photons, but then if you add in 3 kinds of neutrinos and antineutrinos, and with the neutrinos decoupled earlier from matter and than the photons did. And when the neutrinos decoupled from the photons, they decouple. I'm sorry, I'm not saying this correctly. They decoupled from the photons before the electrons and positrons annihilated. When the electrons and positrons annihilated, they raised the temperature of the photons, but the neutrinos were already not interacting and not in equilibrium. And so the neutrinos never benefited from that heating. And so they're at a lower temperature. Anyway, when you add in the neutrinos, you get that the present radiation mass density divided by the present critical density is this number, and that's called omega radiation. And so when you put all those things together, you get that the square of the Hubble constant divided by the present value of the Hubble constant. So I should say the square of the Hubble rate at any time divided by the present value squared of the Hubble rate is the sum of these terms, where these are the ratios of mass densities of the various components. And setting A0 equal to 1, this becomes somewhat simpler. And then, as I said, I should simplify this. I followed Weinberg's trick of setting X equal to A over A0. I think that just makes things more complicated. In any event, you eventually get, so this is an integral that's actually an integral over the scale factor. We're integrating over the scale factor. And one then gets the right answer. If we look at the history of the universe over the past 14 giga years, to use the European notation for that, what we've got is that the scale factor increased fairly rapidly and then more slowly. Of course, I'm leaving out here the initial increase of the scale factor, which is called inflation. So there's a period here. Well, we don't really know what happened back then, but before the Big Bang, there could have been a period of inflation, because what you call the Big Bang is a matter of, is somewhat arbitrary. I think of, if we adopt them, if we accept inflation, I imagine that there was a quantum fluctuation. You had a period of inflation, then you had a sphere, maybe the size of a basketball, that was composed of scalar field, had a very high potential energy. That potential energy then went into radiation. That was the Big Bang. And then we've had evolution ever since. And initially it's going as it goes as, well, let's see, it's going, the scale factor is increasing more quickly initially, and then it slows down, and then it starts to speed up. So so during the initial epoch is called, after inflation, is called radiation. And then since that density is proportional to 1/8 of the fourth, one can show that, well, if you just look at the integral and only keep the radiation part, you get that T is equal to A squared. I suppose we could even see that by looking there. So looking at it, in other words, we would have T of A is, well, 1 over H0 integral 0 to A dx. And the only thing we're keeping is the radiation term. So that's square root of omega r, and that's an x up there. Integrating, we get 1 over H0 square root of omega r, and then x squared over 2, but x squared is a, so it's just a squared over 2. So indeed, as the book says, we find that T is 1 over 2 H0 square root of omega r times a squared. Or equivalently, A increases as a square root of T. So that's the way it's increasing there. Later on, when it's mainly the mass, so the first epoch is when the mass density is dominated by radiation. Then there's an epoch that lasts about 10 billion years, or certainly several billion years, where the mass density of matter dominates. And so then we have the equation T of A is 1 over H0 integral 0 to A dx over, and then it's square root of omega m, and now it's x to the 1/2. And so integrating that, we get a to the 3/2 times a 2/3 H0 square root of omega m T equals. So we get that expression, which I suppose is written down here somewhere. Well, I should have written it down. I should add that. I don't know, it may be buried in here somewhere. Equivalently, it means that A goes as T to the 2/3. And so A goes as T to the 2/3 there. And over here, it's A goes as T to the 1/2. And now you might say, well, 1/2 is less than 2/3. And why is this more steep? Well, the reason is that if you take dA dt, you get A dot is something like 1 over square root of T, whereas here A dot is 1 over T to the 1/3. And 1 over square root of T is bigger for small t than 1 over T to the 1/3. Anyhow, it's steeper here, levels off, and then we have the era of dark energy setting in, when the Friedmann equation is basically h squared, or a dot squared is rho, and rho is E. Rho is, let me see, what do I want to say rho is? A dot over A, well, it's just a constant, say lambda. I'm just saying roughly it's lambda. So let us say A dot is like square root of lambda. And so and that's A dot over A. So A dot over A looks like that. So A dot is square root of lambda A. And so that means that A is E to the T squared of lambda, something like that. So that's the exponential expansion that kicked in around 4 billion years ago. And you can see it just a little bit in this. That's why it was hard to see. But people discovered it just before the year 2000. If we look at the first 100,000 years, then what we've got is we've got the t to the 1/2 dependence more obvious here. That's an obvious square root curve. And it's the first 50,000 years that are radiation dominated. And then there's a gradual transition to an era of matter. And so when finally the temperature drops to around 1 eV, the hydrogen atoms can remain in their ground state, photons then can't ionize the hydrogen gas, and so they don't scatter much at all, and so they just go in straight lines, and that's the CMB. It's the photons that were emitted and around 380,000 years after the Big Bang. And they then were not scattered by the hydrogen gas, and they've been going through the universe ever since. But that happened well into the era of matter, because the era of matter started at essentially 50,000 years. And of course, what's going to happen next is that we're going to have well, there's the A going as t to the 2/3. What I did was I added in the fact that there's a T matter here, which is around 50,000 years. Anyway, the era of dark energy then, if we extrapolate out to 50 gigayears, we're down here at 14. There's the Big Bang. And the era of dark energy started a little after 10 billion years. And it wasn't very visible where we are, but after a while, after around 25 billion years after the Big Bang, it'll become absolutely dramatic and it will expand like crazy. Weinberg made the comment in one of his many excellent books and articles that it's a rather sad future, because it means that if there are any people living at this time, they would see that the other galaxies would be simply going farther and farther away, faster and faster, and eventually the universe would become colder and colder and less dense, and it's sort of a dying universe. Now, what isn't, well, I should say maybe a couple of words about inflation. The idea here is simply that you have something like the era of dark energy, but you have it in spades, namely that in the era of inflation, this lambda becomes huge. So in inflation, lambda is huge, and consequently expansion is extremely rapid. Let me see if I can erase this. All right. So there's a question here. We don't know what. So as for what happened in the very, very early universe before the Big Bang, was it inflation? The other possibility is that it was a bounce, that there was a prior universe that was collapsing and collapsed to very high density, very high temperature, and that was the Big Bang. And that fixes most of the problems that led Guth and others to introduce the idea of inflation. But this big bounce possibility is something that Steinhardt and others have introduced. And Steinhardt was one of the main people behind inflation. And so he's sort of calling in question his own earlier opinions, actually. We just don't know whether it was a bounce or inflation, but presumably in the next 5 or 10 years, we'll understand whether it was inflation, a big bounce, or something else. And presumably in that time, also the tension between the CMV value for H0 and the astronomy, the observational astronomy value of H0 will be resolved. So let's see. What I didn't explain was, well, it's basically that the Friedman equation, of course, looks like this. So if this density is a mass density of potential energy, that's what's thought of as starting inflation. And in fact, that could be what dark energy is. So we don't know what's going to happen in the future. I find it hard to imagine how it is that this expansion is going to turn into a big crunch or a big rip. I don't even know what a big rip is, to tell you the truth. Why don't you send me a link to something like big rip, although I could Google it to find out. I guess I ought to say some things about Yang-Mills theory. The Yang-Mills theory is a generalization of electrodynamics. In ordinary electrodynamics, we have gauge transformations, and the gauge transformation is that a field of charge Q, or maybe minus Q, I can't get the sign right, it's a convention. A matter field that's charged gets a phase factor, and the symmetry is really remarkable in that it can depend upon the space-time point, which is the argument of the field. And this is a pretty remarkable symmetry. You see ordinary symmetries, the kind that, let me try to switch here to, let's say, blue. So in an ordinary symmetry would say phi of x is e to the I theta times maybe q times phi of x, and that's of course phi prime of x. So this is an ordinary symmetry. I do not spell very well, but I'm not going to try to fix that. And the kind of symmetry that was looked upon by particle physicists back 50 years ago, or 60 or 70 years ago, was this kind, where this is a constant. So this is a constant element of a group. And it's a group because, well, whenever you have transformations that leave something invariant, transformations are intrinsically a group. In fact, group theory is, mathematicians should admit that group theory is really just the theory of transformations. What was surprising is that although particle physicists were considering groups like SU2, which are 2x2 unitary matrices, or SU3, which was introduced by Gell-Mann, the symmetry of electrodynamics is this one. And well, it's more profound than that one. It is the one that I wrote there in the book. It's e to the IQ theta of x, phi of x. So in other words, there's an x dependence here. And the reason that that's troublesome is that these theories involve derivatives. So you have an ith derivative of phi prime. This is going to be e to the IQ theta. Well, all right, let me rescue this by using the common notation. But then it's also going to be plus IQ, the derivative of theta times phi. And so the question is, how do you make something like this invariant? For the ordinary kinds of transformations, what you do is you just say di phi, you just have things like this, di phi, and then I'm going back to ordinary flat space-time. And so this is Lorentz invariant. And under a unitary transformation, in fact, let me say that's a complex conjugate, so it's a charged field. Then this thing is, if I use a vector notation now for the fields, it is phi dagger u. But then if u is unitary, u dagger u is the identity. And so this is just equal to phi dagger phi. So in other words, so that's what particle physicists did 50, 60, 70 years ago. But electrodynamics has always been more complicated because the transformation is like that. And the way this is fixed is, let me go. It's to have what's called, instead of an ordinary derivative, you have a covariant derivative. So di of phi is an ordinary derivative plus the electromagnetic field times phi. And now what you require is that under a gauge transformation, as in electrodynamics or any other more complicated theory, this is then u di of phi. Now, if then what you have is you have di of phi adjoint di phi, and under a gauge transformation, then if it transforms this way, what you have then is di phi adjoint u adjoint u di phi, which is just di phi dagger di phi. So that's how it was, how Yang and Mills solved this problem. And of course, what they did was they said, well, we're going to have this, we're going to require that this be true. And the way you require this be true is you just say di phi prime. Well, what is that? That's phi prime, ai prime, because you say di has an ai. This ai is a connection. And so you say di plus ai prime phi I. Phi prime, you know, is U that depends upon X. This might be an SU3 matrix, but that depends upon space-time. And you say, well, that has to be U di phi, and di phi is this. So now you just compare all this. You have that this is equal to that, or equivalently that is equal to that. And what it boils down to is that the connection has to transform this way. And you notice the inhomogeneous piece. Well, this inhomogeneous piece is analogous to the inhomogeneous piece that occurs when the affine connection gamma transforms its various terms times gamma minus some inhomogeneous piece. And that's like this. This piece is like, in other words, this piece is like that piece. And this piece is like this piece. And in electrodynamics and more generally in non-abelian gauge theory, what you do is you form something analogous to the Faraday-Maxwell tensor. The ordinary Faraday-Maxwell tensor is just the commutator of two covariant derivatives. And so you do the same thing here. But now these covariant derivatives are matrices that depend upon space-time. And these matrices are the generators of the gauge group. And so you have di ak minus dk ai, and then the commutator of those matrices. And then what happens is that this Maxwell tensor transforms in a very nice way, which I said is loosely speaking covariantly. And so then the action density of electrodynamics, which is basically E squared minus B squared, you generalize that to the trace of Fik, where the F's are matrices. And since the F's transform this way, and since the trace is indifferent, well, you can move the U to the back of the line here, and then it cancels the U inverse. So it is invariant. Well, we're basically out of time. This was, as I said, done by Yang and Mills back in the 50s at some point. I don't know when in the 50s. Might have been 53. It might have been 57. I don't remember. Okay. Well, I've pretty much exhausted this chapter. I'd be grateful if some of you would send me an email saying what you want to see next week. There's sort of basically two possibilities. One is that I focus on doing some of the general relativity in more detail. Another possibility is that we do some of these topics here. So I don't know. You can look at in the book and think what it is that you might want to see, and if a few students tell me, oh, you want to do path integrals, well, I'll jump and do path integrals. If you want to do functional derivatives, I'll do that. If you'd rather see something about AI or probability, I'll do that. So, but as I said, I'm not a good listener and I'm a terrible psychic. So you got to tell me, I can't read your mind. All right, well, have a nice evening. I'll put this on the web, so I'm going to stop sharing now. Have a nice weekend. And there's a colloquium on astronomy tomorrow at 3:30. Graduate students should listen to all the colloquia. But of course, you listen to as a graduate student, you listen to the colloquium and you give every speaker 15 minutes. If after 15 minutes, you're not learning anything more, leave the colloquium. I mean, you've got a life too. Okay, stop sharing and